Good morning and welcome to Litmus Test. Today we're going to continue our investigation of chemistry math. I know it's spooky, it's scary, don't worry, we can get through it. And last time we talked about the mole and the stack, and today we're going to look at this first half of the bronze reaction. Remember that we have 3 copper to 1 tin will make 4 bronze, or where bronze is Cu3SN. And that's more of a Minecraft reaction than a real reaction, but this chemical formula is real, that we do get 3 copper and 1 tin in bronze. We're going to be using this arc furnace to do that. And this arc furnace works in such a way that if we stick, and I've got it running right now, so if I stick a piece of tin in there, it will smelt this tin down, and in our chest we'll see a tin ingot. Similarly, if I stick a piece of copper in there, it will melt this copper down into a copper ingot. Let's go ahead and get rid of these. I can also put tin over here and copper up here, and this weather will not leave me alone, I said. We can put tin in this corner and copper in this corner, so like this, and that will make bronze. But how much tin to how much copper? Well, if we just have it at a 1-to-1 ratio, 1 tin to 1 copper, we just get a tin. If we try 2 copper to every 1 tin, we still just get a tin. Looking back at our recipe, we see we need 3 copper to 1 tin, and so we'll put in a third piece of copper there and 1 tin. Notice that the bar is a little bit slower, our progress is a little bit slower because we're having a real good chemical reaction. And now we're going to get out 4 bronze. I read it, 4 bronze. Did you see it? Everyone saw it. 4 bronze. Perfect. All right, so we know how to make copper and bronze. Excellent. But how much could we make, like, for some tin, or for some, like, which of these goes farther? Which of these do you need to mine more? Which do you need to have more of to make the bronze? Well, let's get rid of this stuff. We'll toss this, and we're going to toss in to our arc furnace a stack of copper and just a whole bunch of tin. Whole bunch of tin, lots of extra tin, but only 1 stack of copper. Now, because that's both in there, we should get some bronze. Let's see if we can figure out how much that's going to make. All right? Well, we know that it's going to take 3 copper and 1 tin to make the 4 bronze. So we know that we're going to start with 64 copper. All right, so we have 64 copper. In fact, let's say we start with 1 stack of copper, because that's what we did. We started with 1 stack of copper. We know that that's 64 per stack. And then we're going to put a division here. You'll see why. We know that, so now we've got it in atoms of copper. We know that for every 3 copper, we get 4, I said 4 bronze. So for every 3 copper, we get 4 bronze. Notice that I'm using this as a per, or for this, for that. This for that is division. And then I say we get, and I'm using multiplication. So 1 stack of copper is 64 copper per stack. And for every 3 copper, we get 4 bronze. We can type this out in our calculators like this. 1 times 64 divided by 1 for the stack there, divided by 3 times 4. And that's just 1 times 64 divided by 3 times 4. Easy peasy. Kind of. 64 divided by 3. Well, we saw that last video, right? We saw that last video that was 21 with a little bit left over. 21 with a little bit left over times 4 should give us 84 with a little bit left over. So let's see if we get 84 bronze coming out, or a little bit left over. And we can also, we know that we have 84 bronze, we could say, well, divided by 64, we get a stack, and that should give us 1.33 stacks, 1 1/3 stacks. You can test that out for yourself to see if the math works. But let's check here our copper isn't quite done yet, but it will be done in 3, 2, 1, and here we go. We've gone through our full stack of copper. We've actually gone a little bit extra on the tin. So let's see, get rid of this tin. Ooh, we went very far extra on the tin. We've got exactly 84 bronze ingots, or just under a stack and a third, because remember 21 is the third of a stack. That's exactly what we expected to get from our calculation, right? And we, if this were a mole, if we were using moles and we were instead of stacks, then this little bit of copper grit would have been just, one little piece of a mole, one little fraction of a mole, and it would have been used up along with all of this. But since the analogy here isn't really to moles, it's to atoms, or, well, a single piece of copper is like an atom. One atom will not react with one atom of tin. One atom of copper does not react with one atom of tin. It takes 3 atoms of copper to react with 1 atom of tin. So yeah, even though it might have given us exactly 1 1/3 moles, in practice, and this is actually a really important thing in chemistry too, in practice we never get exactly what we want to get. We call that the theoretical yield versus the actual yield. In this case, our theoretical yield was 84 point something something something, or maybe 85 point something something something, 1 1/3 stacks. And here we have 1 and slightly under a third with this little guy left over. So we can say our actual yield was a little bit lower than we expected. But that's okay. Let's just go ahead and replace our supplies, because now we want to ask the opposite question. All right, we want to ask the question, let's let that sort itself out, no extra tin in there. Let's ask the question, what happens if we have 1 stack of tin and just lots of extra copper? Okay, yep, that's going. There we go. So 1 stack of tin, lots of extra copper. Let's clear this around. And remember that we have, right here, 1 tin to 4 bronze. All right, so we have 1 stack of tin, and we know that that will give us 64 tin per stack. And we know that for every 1 tin, we get 4 bronze. All right, so that's just 1 times 64, divided by 1 times 1 times 4 equals, well, that's just 64 times 4 right there. That's 256 bronze. 256 bronze, remember, for every 64 atoms, we get 1 stack. Well, that's just 256 divided by 64. Let's just look at that. The 64s cancel out. We just have 4 stacks remaining. So we expect to get 4 stacks. 4 stacks off of the 1 stack of tin that went in. As we can see, it's going real quickly here. Yep, that's certainly going. But when we're done, we expect to have 4 stacks of bronze out compared to the mere 1 1/3 stacks of bronze we got for a whole stack of copper. So you notice right away that in this reaction, if we had just equal amounts of copper and tin, you notice that it seems like the copper should run out first. The copper makes less bronze. It runs out before the tin does. In fact, that's why we've added so much extra copper here. Hopefully this will be way more than we need, which it should be, right? We only expect this to use up 3 stacks, right? We can actually check that too. 1 tin to 3 copper. So 1 stack of tin should use up 3 stacks of copper. And in this situation, our tin is going to be the one that runs out first. In the first test, we made sure the copper ran out first. The thing that runs out first is called the limiting reagent. It is the stuff that runs out first. It limits how much stuff you can produce. Limiting reagent problems show up all over the place, and you should assume most of your problems are limiting reagent problems, especially when you're given there's some amount of thing and some amount of other thing, some grams of copper and some grams of sodium. Assume it's a limiting reagent problem and start working on figuring out what the limiting reagent is. You can tell by doing a quick little calculation, kind of like we did here, but instead of going copper to tin and tin to copper, you're going to go the tin to bronze and copper to bronze, and you're going to do the same stuff that we just ran through here. We're going to figure out how many stacks, or how many atoms, but generally how many stacks you expect to produce. Given that that calculation was for 1 stack of copper and then 1 stack of tin, we know that copper only makes 1 1/3 stacks of bronze. We think that the tin is going to make 4 stacks of bronze. We'll see how it goes. So we would predict that the copper is the limiting reagent. It runs out first, and it will produce the lower amount of product. When you're doing a limiting reagent problem, look for the lower number of moles if you use up all of your first reagent or all of your second reagent. In other words, do this math for however much tin, or whatever your reagent is, to your product, and then do the same math for the other thing to your product, and put them both into moles. Ideally, you want to do something like I've done here. Ideally, you want to put as much as possible into one line of calculation so that you only have to push the equals button once on your calculator, and then you're done. Let's wait a little bit and see if this really does make the 4 stacks, just to make sure that we've done our math correctly. In 3, 2, 1, ha! Now we're done with this, and we didn't kill the video this time, so that's excellent. This is the 3rd time I've shot this, but never mind. We started with 1 stack of tin, and we've got 4 stacks of bronze, 256 bronze, which is exactly what we predicted to get. 4 stacks of bronze. So, let's review. We can take stacks of copper and tin, turn them into bronze. We know how to do that. We know exactly how much we're going to get out. 1 stack of copper gives us 1 1/3 of bronze-ish, and 1 stack of tin gives us exactly 4 stacks of bronze. This means that we've got a theoretical yield here of 1 1/3 stacks of bronze, but an actual yield a little bit less than that, and we could put those over each other in like a percentage and get a percent yield at like, I don't know, 93% or something. You guys can do the math on that. But the point is, it's a little bit less than what we got. Our theoretical yield on the tin was 1 stack of tin made 4 stacks of bronze, and you'll notice that our theoretical and actual yield are perfect. Again, we can do a percentage and get a percent yield, and our percent yield is 4 stacks. Look at that. We've got 4 stacks of bronze, just like we predicted. And all of that just by doing a little bit of math there. So as the sun rises, oh goodness, it's been all night long. Well, not for you guys. Well, as the sun rises, we've gone over how we do stacks and reactions. We've talked about yield, percent yield, actual yield, theoretical yield. We even touched on limiting reagent. Which of these things will make least, or the least, amount of stuff? Limiting reagent is a little tricky. You always have to do a little bit of math first to say, if I have this much copper and if I have this much tin, how much stuff am I going to get out? It's not enough to say that, oh, well, I always, that copper will always be the limiting reagent in this particular problem, because it might not be. It might not be. In this case, tin is clearly the limiting reagent. I will run out of tin long before I run out of copper here. Likewise, now I've got way more tin than I need copper. Even though the ratio is 3 copper to 1 tin, the amount that I put in really does matter. So you'll have to do those calculations for yourself whenever you're faced with a limiting reagent problem. But with these ideas in mind, and with this basic idea for the math down, we can see how we're going to solve the next question in the next video. So stay tuned. Thanks for watching, stay safe, and don't catch on fire.